Today, guys, we are going to talk during this session. I'm not going to overflow you with the information about Apache Ignite only. Probably many of you have already visited a lot of conversations presented by my colleagues and different community members of Apache Ignite. But today I want to talk about a specific use case, a specific scenario of usage of both Apache Ignite and Apache Spark. I want to show how I want to propose an architecture that is feasible to implement in production. And that architecture is suitable for IoT applications and services. And for sure, we are going to use the software developed by Apache Software Foundation, such as Apache Spark and Apache Ignite. So a couple of words about myself. My name is Dennis Magda. I'm Apache Ignite PMC chair, and at the same time, I'm taking a role of GridGain's Director of Product Management. However, I joined GridGain and Apache Ignite community a decent time ago as a software engineer and still pretty technical guy who can answer on all the tricky questions you might have during this session. So let's move on. Oh, that was the wrong button. This one. So our agenda for today looks like this way. First, before we start looking at the architecture, I want to discuss the main demands. What are the demands that are coming from the IoT use cases to your software that you are going to implement and deploy in production? Next, once we figure out the demands, it will be easier for us to build a software, a service, a backbone of our IoT architecture. And basically, I'm going to split this architecture in 4 main building blocks. The first one will be an operating system that has to be installed on your edge devices, or also under the edge devices, I mean all those things from the Internet of Things, like smart meters, like sensors, smartwatches, different and other different tools that can measure information around you and transmit this information back to your service. Next layer will be the layer that is directly connected to your, let's say, sensors. Let's take sensors as an example for our architecture. And this layer is going to pull data from your architecture. Once the data is received from your architect, from your sensors, you need to store it somewhere so that you can reuse it later for your business needs. And here I'm going to use not a conventional relational database or NoSQL database. I want to propose a so-called new SQL database. And finally, before we go forward with any kind of device operating system or data collection layer or new SQL database, we want to be sure that all the APIs that are provided by this software are enough for our applications to build services on top of that. And finally, at the end, I will show you a quick demo. I prepared a special template, source code template that you can use. You can start with it if you want to use both Apache Ignite and Apache Spark and write something useful, something workable for your own needs. Well, talking about the IoT demands. First thing, usually if you take a look at this picture, you will find that Internet of Things consists and encompasses a variety of different appliances. It can be different fridges, it can be ovens, microwave ovens, or it can be something that really needs real-time guarantees, such as self-driving cars, for instance. Just imagine a use case that you are driving behind the wheel of a self-driving car, probably produced by Tesla Motors or BMW, and the vendor, the manufacturer, is responsible for your safety. And this safety is ensured by a variety of different sensors that are deployed in this car, and all these sensors deliver information to a central processing unit in real time. And here is neither sensors nor the central processing unit central processing software in this car cannot afford any delays, any violations of any SLAs. This is where real-time requirements. This is when real-time requirements become essential for a variety of different IoT applications. Next requirement. The guys who are going to develop a software for an IoT use case, they are not that unique from other backend or web services developers. They still need to use some advanced querying APIs. And here is, I cannot come up with better querying or the better advanced querying language such as SQL, for instance. That language proved to be a sort of standard for advanced queries in the recent decades. And why not to keep using it for our new architecture and not reinventing the wheel? Also, for IoT use cases, when you are going to measure, gather, and transmit geolocation information, such as geolocation when you run on a trail and you want to gather some statistics about your kind of experience, how far you will go during this workout. All this information is also measured by your smartwatches or your wristband, and it will be processed and probably transmitted somewhere. And also, if you need this functionality, you need to be sure that your architecture is able to do two things: both store geolocation information and provide APIs that are needed to query this information efficiently. Next, IoT use cases such as created for self-driving cars or for different robotics applications, they require more than SQL, something more powerful, something more strong, such as analytics functionality. And here is we might need to get some AI or machine learning APIs to be available in our platform, in our architecture. That might be optional, but anyway, this is something you might consider depending on your use case. Next thing, we are living in the 21st century. And now high availability is no longer a nice feature to have for our infrastructure. We hear a lot of different talks that are presented by folks from the financial institutions or from telecommunication, from from logistics and transportation. All of the folks, they tend to speak about the high availability. That's because this is no longer just a nice feature to have. It's a requirement of nowadays. We want to be sure that our IoT infrastructure architecture will be highly available all the times, no matter what happens with our service. Unless all our data centers are destroyed, we want to be sure that our applications and our infrastructure is up and running. And finally, the next demand that is being driven by the IoT software is simple scalability. So we know that possibly it's possible to scale up different architectures. Like you can take a relational database and you can upgrade it to the next generation hardware if you need more CPU units or more memory space. But it's no way to go for you if you expect to get more and more data to be pushed to your architecture all the time. You want to have such a database, such an architecture that is capable of getting all this data and scale on demand, simply. Simply, I mean that preferably we want just to add a new machine to your distributed database, and that machine should become a full-fledged participant of your distributed cluster in a matter of minutes, taking some data sets for storage and processing workloads. So here are the demands and how their proposed architecture might look like. This is the simplest building blocks that I came up with in my mind. So first, starting with the lowest layer. Here is we have an operating system. Like here is we have an operating system that you need to install on your sensors, for instance, on your smartwatches. If your let's say, sensors on your edge devices are powerful enough, you might be lucky one, and you could install Linux operating system, like embedded Linux. But in the most scenarios, when we talk about smartwatches or sensors, people have to install real-time operating system. And this real-time operating system is usually installed on a really, really constrained hardware. So how constrained it can be? I brought here a simple example for you so that you can grasp visually how the hardware can be constrained. So here we have a prototyping board. Usually this is the board that is used by embedded developers. When they want to write some applications, as other Java developers, they need to install an IDE, but at the same time, they need to have all the pinouts, all the connectors to be available for them so that they connect different sensors like this one to this board. But the operating system is being installed on this tiny block. And this tiny block includes everything you need, like CPU, like RAM, flash, and probably some networking components. And usually this microcontroller has around, it might have, this one particular has around 64 kilobytes of RAM, and it has around 1 megabyte of flash. And this will be enough for you to install an operating system, real-time operating system. And even more, on top of that, you can write and deploy your applications. So this is what the guys from the embedded world have to deal with. Here we are talking about the big data, but this is how your IoT application starts. This is how it starts its lives from these tiny devices. Next, when you develop your application, once you go for an operating system, you need to, you deploy these devices, you've written an application, and now you need to transmit all the information from these sensors. And here we probably need to use special data collection and enrichment layer. This a framework or library that is presented in this layer should connect over the network to your sensors and grab all the data from there. It's simple. And enrichment means that before you put this data into your final storage, into your database, you might need to enrich it, adding some useful payload, like you might need to add a timestamp, or you might need to add some special IDs, identifiers to your measurements, doing all this stuff. And finally, once the data comes to your database, here is you might get a lot of different APIs that are needed for your applications written on top. And why do we need to use new SQL database? Simply because that type of database supports all their guarantees, all the demands that are usually driven by IoT applications, such as real-time processing, simple scalability, high availability, and for sure the APIs, such as SQL. This is all you can get with a new type of databases that sometimes are marked with new SQL database. Okay, and today I'm representing Apache Software Foundation here, and I'm going to suggest you the products developed in-house by a variety of different community members who work for Apache. So first, as a device, real-time operating system, we are going to use Apache MyNewt. That's a relatively new top-level project at Apache, and that's the only one real-time operating system that belongs to Apache Software Foundation, and you can take it and deploy it and use it for free, as any other project that came out from Apache. Next layer, that layer is it's much broader. Here we have a variety of different frameworks that can be used as data collection and enrichment layer, such as Apache Flink or Apache Spark or Kafka. My preference would be to use Apache Spark. That's just my preference, but then it's up to you what you decide to use in your scenario. Finally, speaking about the new SQL database, if you take a look at all their platforms and databases that are released under their Apache Software Foundation, you will find that Apache Ignite is the only one that can be used as a new SQL database, simply because of the variety of capabilities that we are going to. Some of them we are going to review today, but probably I guess that you heard a lot about that throughout these 2 days of the conference. And finally, speaking about the backend application, your services, your web applications. Here is you will be able to use not only Apache Ignite APIs, but Apache Spark APIs, because both frameworks are integrated with each other. So now let's briefly look at every component, starting with the lowest level. Apache MyNewt. So actually, Apache MyNewt, again, it's a real-time operating system that can run on hardware that is powered by CPUs produced by ARM Limited, such as Cortex-M family, Cortex-R family, and many others. At the same time, they do support other CPUs lines, such as MIPS, for instance. And once you install this operating system, you as an embedded engineer, you can use multitasking. You can store data in memory, you can allocate memory, you can connect to your flash system, you can connect to your sensors, you can connect to your temperature, I don't know, other type of sensors from your applications. And what's more important, once you have written that application, that, for instance, gathers temperature in the area where a sensor is deployed, you are able to transmit it, because this operating system provides all the basic networking APIs that are needed for you as an application developer. Such as you can write you can open standard TCP/IP sockets or UDP connection, or also you can connect over Bluetooth or Wi-Fi or Ethernet, depending on your needs and depending on your use case. Next, when it comes to the operating system and application flashing into this hardware, you can flash all this data securely, not worrying about any malicious intervention from the outside world, because all the binaries, they can be how do you call it? They can be signed. And during the flash time, the operating system can double check that all the code that has been flashed into it is kind of proved to be that it's coming from your application developers and not from someone else. And final thing, when it comes to application and operating system upgrades, for sure you don't want to go to the field and to take all the sensors deployed there. You rather want to connect to those sensors remotely and update all the software sitting in your office. And here is, like many other real-time operating systems, Apache MyNewt allows you to connect, let's say, to your sensors or to your smartwatches and upgrade all the software remotely. That's what you can get. Okay, once you install Apache MyNewt on your sensors, and once you created an application that, for instance, gathers temperature around, you can transmit it over the network to the next layer, which is data collection and enrichment layer. And here is probably Apache Spark is one of the best options to use, because Apache Spark has so-called Apache Spark streaming component. That Spark streaming component allows you to deploy a variety of different streaming chains. And you can, from Spark, you can directly connect to your sensors deployed somewhere, and you can start receiving data in real time, continuously or endlessly, and process it once the data comes to your Spark streaming module. Once Spark receives all this data, you can directly on the Spark side enrich this data or transform it, adding some payload such as a timestamp of a measurement. And finally, once you're done with this part, you can push the data back to your database, which will be your Apache Ignite cluster, if to refer to this architecture. And speaking about the Apache Ignite, How many of you have seen this slide before? Oh yeah, 50-50. Yeah, I'll be short. I want to show you more code than repeating all this material over here. So in general, why Apache Ignite can be used as a new SQL database? Why is it so? First, because of its memory-centric storage. Memory-centric storage implies that Ignite uses both RAM and disk as memory tiers. So if you can fit all the data in RAM, that's great. It means that you will get benefits of in-memory performance. At the same time, all we need usually is the durability, and once you enable disk layer, you will never lose your data. This is what you get. And on top of this memory-centric architecture that is distributed by nature, so all this memory that is available, that is shown on this picture, is supposed to be distributed across a cluster of machines you have. You can use a variety of different APIs without any limitations. Like for the IoT scenario, in my personal experience, it would be useful to use SQL, compute grid, and machine learning, depending on the complexity of a solution you are building. Next, and if to take a look at these capabilities, some of the capabilities that are relevant for our IoT applications. Okay, as for SQL, so again, here is once you deploy your cluster, you can start using it in a way you like by running computation, machine learning calculations, or you can run and execute your SQL queries. Speaking about SQL capabilities, Ignite implements so-called NC99 SQL specification, meaning that all the functionality that is supported and listed in the specification is implemented and delivered by Ignite. For instance, you can execute well-known select, update, insert, or delete statements, and even more, when you select your data, you can run distributed joins. Like this is something that is not always supported by other distributed systems. This is what you can do with Ignite. And as for the connecting APIs, you might know, guys, as I see there are many folks who saw that slide at least, and probably this one. Here is, I just want to point out that Ignite is written in Java, but you are not limited with Java programming language. If you're a .NET user or C++ user, that you can use specially developed native libraries for Ignite, or if a Python or Ruby are your favorite languages, then you connect to the cluster using ODBC or JDBC connectors and query it, manipulate, and process the data using SQL syntax. Well, that's SQL. However, for the IoT use cases, SQL and other, querying APIs, they're pretty nice because they can help us writing some complex queries that will do some analysis with the data. But the problem here is that sometimes those queries might return a pretty big result set back to your application. And you start moving a lot of the data from your cluster to your applications. Sometimes it's not needed, and sometimes you can lower down the noise on your network by applying so-called collocated processing techniques. In Apache Ignite, we have a component called compute grid. So compute grid is the same thing as a MapReduce in Hadoop and fork join framework in Java. So what it gives you, you can create different computations. Then those computations might be split into a number of subtasks or jobs. And all of these jobs will be executed across a cluster of machines you have, or only on those machines when you keep a specific data set. And the benefit here with this collocated processing approach is that you avoid data movement across your machines. Here is it support that you will get back some tiny result set. But with SQL queries, as you know, a result set might be pretty big in size. Spark. So we talked about Spark, and I suggested to use Spark as your data collection layer, but at the same time, you can keep using Spark, even now, you can keep using Spark RDD APIs once your data gets delivered to Ignite. Ignite implements Spark RDD's interface, which means that in practice, a Spark RDD interface is just one more method to work with the data you store in your Apache Ignite cluster. So like if you like Spark, if you like RDD's APIs, then just you can connect to your cluster from Spark. You can get a reference to some data sets stored in Ignite, and you can process those data sets using their APIs written and supported by Spark RDDs. And even more, on top of this, as you know, Spark native RDDs, they are immutable, meaning that once you get an RDD, you will not be able to reuse it among Spark workers, like over here. And you have to recreate an RDD all the time if data is being updated. But with Ignite shared RDDs, an RDD will be shared across all Spark workers you have. And it will be mutable, simply because a shared RDD is just an interface on top of Apache Ignite data that you store. And if you try to update anything using Spark RDD interfaces, it will be immediately updated in your cluster. And all the other Spark workers, they will see these modifications. And final, probably the most advanced APIs that might be required for our IoT applications are useful for business intelligence and machine learning. So on top of this on top of our distributed storage, and by leveraging our compute grid, which is our MapReduce framework, Apache Ignite community started building its own machine learning component. This machine learning component is natively integrated with the overall architecture of Ignite. And a gateway here is distributed core algebra module. So that was the first thing that was developed and released by the community. And actually what it gives you, you can do different operations with matrices, you can do different calculations, and once you start storing data in your Apache Ignite cluster, your different calculations, we will be able to distribute it in the most efficient way. And on top of that distributed core algebra, we started building different well-known and needed algorithms that are applied in everyday life of every data scientist, such as k-means clustering, linear and logistic regressions, and so on and so forth. However, this module is still in the beta state, so it's being actively developed. And if there is any of you who is willing to try it on for its own use case, I would encourage you to come to our Apache Ignite community, give it a try, share a feedback, and even more, if you're a data scientist or if you're just curious about different machine learning stuff, it's a good chance for you, to come and to contribute something, because here is you can improve your machine learning developer skills, because we are looking for here, we want to have as much algorithms as possible. And there is a lot of work to do if you're interested in this. Well, that's all from theoretical part. Let me quickly show you the application I prepared for this talk. Okay, here I have a simple application. In this application, I'm going to start a couple of Apache Ignite nodes on my local laptop. I'm going to do this from this IntelliJ IDEA development environment. But anyway, you can do this from a command line, or I don't know, it's up to you. Here is for to shorten our time, I want to do this directly from this IDE. Okay, my first node is up and running, my second node has connected. Unfortunately, I don't know how to increase the font size here, so sorry for this small font. Now I want to check that I want to use Apache Ignite Web Console throughout this demo. So that first I need to start this Ignite Web Agent. It's a special application. It's a sort of a mediator that stays between my cluster, my local cluster, and a web console deployed somewhere. And as for the Apache Ignite Web Console deployment, I'm going to use the deployment hosted on GridGain infrastructure. But you can go ahead and download this console and deploy on premise or in cloud, whatever you like. Okay, let me see that my cluster is up and running. I just want to get a confirmation from this web console. Okay, here I have two of my cluster nodes. The CPU is underloaded, no GC, nothing like that. You have some different memory characteristics. And here is in this simple demo, I came up with the following use case. I'm going to deploy several sensors worldwide using some random algorithm. And then all those sensors are going to push different temperature measurements back to my cluster via Spark. And now, as we can see, the caches, or the tables in the relational world are deployed in the cluster, but there is no data yet. Next step, we have our simple Spark application. Let me show how it looks like. How many of you are familiar with Spark? Okay, a few folks. Okay, good. So anyway, here is we are doing some standard Spark related things. We need to create Spark configuration, prepare Spark streaming context, doing some manipulations with the login engine. I just don't want to show all the messages produced by Spark. And then here is an interesting thing. This is how I connect from my Spark application to my to my Ignite cluster. Also, I'm providing a special configuration. Usually, this configuration includes only network-related parameters, so that this application is able to look up my cluster deployed locally and connect to my server nodes, to my nodes that are going to store data. Once this happens, we already seen, guys, that there are already two caches deployed, right? First is sensor cache, and the second is temperature cache. And here is from Spark. I want to get access to those data sets. And this is how I do this. I need to use Ignite context, call it from Spark, and this access will be driven by Spark RDD's APIs. That's just an implementation of Spark Java RDD API. So once it's implemented, you can use all the APIs provided there. Finally, once I'm connected, I want to deploy and preload information about some dummy sensors around me. And here is I have this dummy source code. So I'm going to have 1,000 sensors, and I'm going to put them in various locations worldwide. I don't know. And every sensor will have a unique ID and some latitude and longitude. That's all. I'm going to populate a special array list with this data, and once this data is ready, I'm going to use this method. I'm going to create a Java pair RDD and save this RDD into Ignite. That's the point when Spark pushes data into Ignite. And then Ignite will take this data and spread out across those two local nodes that I have here running. Both nodes will store this data locally. Okay, so let's start this first. And while the Spark is being connecting to my cluster, I want to show you the second. No, I'll show it to you a bit later. I don't want to overwhelm you right now. There is too much code to show. Okay, so here you see that Spark has already done with all its own internal setup. And now Spark is connecting to Ignite. That's a standard Ignite output. Okay, Spark connected. Don't pay attention to this exception. It's expectable. I'll explain later why you see this exception. What I want to show right now we should see that, now we have all these 1K sensors deployed in my Apache Ignite cluster, but there is still no any temperature information because nothing gives us this information. I plan to write a simple application for this guy, but unfortunately I was out of time, and today I just prepared a special simple Java application that is going to connect to my Spark cluster and transmit some sample temperature measurements to Spark and then to Ignite. And exactly this, unfortunately I cannot scale it out. This error says that Spark is trying to connect to this localhost port number, but the connection is being refused. And actually that's the localhost port number of my sample application that is going to generate all this temperature information endlessly. In the real world scenario, that will be a port number or address number probably of your of a gateway that is connected to your sensors, to your hardware. And over that gateway, you are going to get data from your sensors to your Spark application. Well, and this application is here. It's a simple Java application. No, that's not. I called it sensor data generator. Here is, it opens server socket connection. It accepts the connection of this port number, and then we are going endlessly to generate different temperature information for the sensors we have. We know that there are 1K sensors, and we are going to pick a sensor randomly, and we are going to pick a temperature randomly too in this range. That's all. Okay, let's quickly start this application. Okay, it says it could connect to Spark, and now if we go back to Spark, we will see that this exception disappeared, and instead we see some other output. What kind of output we have here? Let's look into the source code. That's the next method, stream sensor measurements. What we did here, Spark connected to that application, and then Spark starts receiving raw data endlessly using this stream method. For every data that we receive, every data sample is encoded in a string. And Spark is going to split this string first into latitude and, it's going to split it into the ID on a sensor ID and the temperature. And finally, it's going to push this information further into the streaming chain deployed on Spark. And here is we are going to enrich this data by the timestamp. This is how you do the enrichment. All these loops are executed simultaneously in parallel. And finally, when the data is collected and enriched, it will arrive to Ignite over this temperature RDD method. And this temperature RDD, as you remember, is just a connection point to your temperature data set that should reside in Apache Ignite cluster. And here is, and once we start this, all this data is being moved endlessly from sample application, Spark, and Ignite. And if you go back to my console, here as we see that we already have almost 1K of different measurements, and it keeps growing. And finally, other interesting thing to show here is that from Spark, directly from Spark, now you can run Ignite SQL queries, getting benefits of all the indexing capabilities Ignite has. And here is from Spark, I studied a special timer that is going to execute, that is going to give me a number of sensors that reported the temperature in this range. I'm going to group them and to sort them. I'm going to do this operation once a second. And here, as you can see, ID of a sensor and how many times that sensor reported a temperature between 70 and 100 degrees Fahrenheit. But at the same time, this is what we do from Spark. It's over here, this way.
From the cache.
From the cache. And finally, I can do the same, like I can execute the same queries from any other application. It shouldn't be only Spark. Let's say I can go to the same console, and here is I have some queries, like I can run the simple SQL query, getting the maximum temperature reported so far, and turns out to be that the temperature is 109 degrees. And also I can run some advanced queries with joins. Here is we are going to join data stored in temperature and sensor tables, so temperature and sensor caches. And specifically I want to get the measurements reported by sensors deployed in the United States continental boundaries. I'm going to filter out the rest of the sensors that can be deployed in Europe or other locations in the world. And here is what you can see. Here is we are getting an ID of the sensor and maximum temperature reported by this sensor. Okay, so here is what we get, guys. This is what we have. And basically, I hope that you kind of grasp the main idea that even if you start building an IoT-based application, basically you have a lot of variety of frameworks and tools around you, and all of those tools are available for free. Moreover, they're available for free. If you're fine with the software provided by Apache Software Foundation, then go ahead. I will be luckier. I'll be pleased if you prefer Apache Software Foundation software. But at the same time, you have a variety of other choices. And as we found out during this conversation, you can really easily to build an application like that quickly. And you can deploy a cluster of Spark nodes, Ignite nodes on a local laptop and run this application in a matter of, in a matter of hours. It took me 1 hour or probably 30, 40 minutes to develop this whole application. So I think that I have around 5 minutes for the questions because I'm going to have the next talk, the next door. Yeah.
Dennis, so thanks for showing the Spark IoT middle layer. But we all know that there are other applications which have the jet streaming, right? Hazel Gas has that, and maybe somebody else comes in the future. Is that easily portable to allow that streaming application to be pluggable before Ignite?
Yeah, you can do this. You can do this, and even more. Ignite also. Some of you might know that Ignite also has its own streaming capabilities. But usually, when people ask me why don't you use Ignite streaming capabilities, why do we need Spark? Usually, I say that Spark, like Kafka or Flink, they are more advanced in terms of streaming because those are streaming products. While Ignite provides some essential things like you can stream data efficiently into Ignite, and you can process simple callbacks. But when you need to build different streaming chains like this one we did in Spark, then it's better to use Spark because it's more advanced. Ignite is evolving in a direction of a distributed database, not a streaming system like now. And presently it pays more attention to, I know that the community pays more attention to performance of disk, of memory, of SQL, and machine learning. As for the streaming, we prefer to integrate with an existing products, like Kafka and Spark.
Could you please recap on your example, because I couldn't follow you, it was pretty quick. It seems to me you started 3 separate Java processes.
Yeah, let's double check. Yeah, I studied 4 Java processes. Yeah, the first 2 are for Apache Ignite nodes.
So it was two separate processes to start. Okay.
Yeah.
Then there was a feeder.
Yeah, this one sensor data generator, right?
Yeah, there was a simulator and there was a Spark.
Yeah, 4
feeds into Ignite.
Yeah, 4 applications in total.
And what was the application that actually showed visualized the video?
That's Apache Ignite web console.
Oh, okay, so it was.
Yeah, it's deployed presently. This one instance is deployed, hosted by GridGain.
So if instead there was a client application for data visualization, whatever, do you still recommend this setup when you run basically Apache Apache cluster is a separate thing from the client application?
Yes, so here is what I had, my Spark application connected in so-called client mode.
Right.
Yeah. So the rest two nodes I studied locally, those are server nodes, those are data nodes. The data nodes store data sets and process workloads, and we want to avoid their restarts in general. So we just want to start them once and put all this data and let them live this way. But when you want to update your application, you just need to restart your application, restart the connection to the cluster. It's simple.
That's generally the preferred mode.
Yeah.
Because you could actually
Yeah.
start your business application.
Like think of like server nodes are needed for you like when you think of MongoDB or Cassandra or relational database, you have a database process. And here is in my example, a database was my two server Ignite nodes. And then separately I have some connections from applications. Like here is I use some special client connection from my Spark application, or like I connected over JDBC from this web console. This is what I did.
And also Ignite, you can use the in-memory within the application. If the client wants to use the in-memory not as a cluster, you can still use it, right?
You can cache some data. We have near cache stuff for our client applications. But usually clients, the main difference between clients and servers, that servers are your data storage, while clients is just your gateway to your cluster. And usually we don't store, you can cache some data, but usually.
And clients can pull and push, right?
Yeah, clients is just, all the APIs you can find in Ignite. It's supported for both clients and server nodes. You just, like your access to the whole range of APIs available in Ignite. Okay, guys, so I need to run to the next door. So if you have any other questions, you can catch me around here, or you can attend the next talk, and I'll be able to answer on the questions you might have. Thanks a lot. SQL.